Well, welcome back to the 5-day CCDA Bootcamp. My name is Anthony Sequeira, and you are tuned in to the one and only Internet Work Expert. We're thrilled that you're back here with the CCDA Bootcamp, and we are going to continue our discussion, as promised, of IPv6. In the last lesson, we went ahead and we took a look at IPv6 addressing mechanisms. It's so famous. Everybody wants to talk about addressing. But we know there's a lot more to the routing protocol than just, there's a lot more to IPv6 than just the addressing. In this particular section, we're going to take a look at the routing protocols for IPv6. And we're also going to talk about something that is critically important, and that is, how are the various ways we can transition to IPv6? Let's face it, we know that we can't just flick a switch. We can't just send out an email to everyone saying, hey, next Tuesday the internet's going to be taken down while we migrate to IPv6. So we're going to have a lot of rich transition mechanisms for this particular technology. First of all, Cisco routers understand they don't run IPv6 by default. So you have to go to a Cisco router and you have to enable this capability. Cisco routers are what we call dual homed by default. Okay, Cisco routers do have the ability to run IPv6 right on top of the interfaces that are running IPv4, no problem. They can do that by default. But as far as the router's ability to actually run a routing protocol, that is going to be something we have to turn on. By the way, I just mentioned an important concept there, the concept of dual homed. Okay, so dual, another way you refer to it is dual stack. Dual stack refers to the ability to run both IPv4 and IPv6 simultaneously. Now, dynamic routing, by the way, you could do static routing if you wanted to, of course, but we're most excited by dynamic routing protocols. Notice there's a version of good old-fashioned RIP that is appropriate and workable for IPv6. It's called RIP Next Generation. There's version 3 of OSPF that is a possibility for you to use with IPv6. The TCP/IP version 4 option for OSPF is called version 2. So they incremented the version number, and that's what we've got for IPv6. They created an EIGRP version for IPv6, and they labeled it EIGRP v6. And then, very interesting, the intermediate system to intermediate system protocol, as well as BGP, they really didn't need to be modified in order to run BGP. So they can do, in order to run IPv6 rather, so they can go ahead and route for IPv6 kind of by default. That's a bit of an oversimplification, but just realize that those protocols were built with extensibility in mind. So those protocols, because of the unique way in which they were constructed, we don't have to worry too much. There wasn't much that had to be done in order to route v6 traffic over those protocols. Many of the issues that we have with like name resolution in NBMA environments, those issues still exist in IPv6 worlds. One of the things that's interesting is these dynamic routing protocols, they recurse to those link local addresses we talked about in the last lesson. So when you look at the routing table on an IPv6 router, you're going to see that the next hop is going to be the link local address of the neighbor. Pretty interesting there. So link local is used for the next hop. So like I said, one of the options that you have for routing IPv6 is static routing. Static routing. You can point to the next hop, you can point to a multi-point interface, or you can point to a point-to-point interface, and you can implement IPv6 static routes. You can use RIP Next Generation, or you can use OSPF version 3, or you can use EIGRP version 6. Notice these are all unique new routing protocols that work independently of the IPv4 versions. They run in a completely separate process on the device. BGP and ISIS, they are exceptions to this rule. They actually route v6 traffic under the same exact routing process as the v4, but they use the concept of address families. So we go in and we configure the v6 routing under what's called an address family. But in the case of RIP Next Generation, OSPF version 3, and EIGRP version 6, it is indeed a separate routing protocol process in order to move the v6 traffic. RIP Next Generation, sometimes simply called RIP for IPv6, by the way. RIP Next Generation was specified in RFC 2080. And the beauty of these routing protocols is once you master RIP version 1 and then you master RIP version 2, then it's very easy to understand and work with RIP Next Generation because there are more similarities than there are differences. I mean, it's amazing. Remember when we said earlier that RIP version 2, for instance, would use the multicast address 224.0.0.9 in its updates? Well, look at the multicast address that is used by IPv6. It ends in a 9. That's no coincidence. They wanted you to be very familiar with this. Okay, they wanted you to feel as comfortable as possible when I think my mic might have just gone out for a second there, but let me just repeat, just in case it did, what I was saying. Yeah, they want you to feel right at home, right? RIP version 2, 224.0.0.9, and then we have this next generation using FF02::9. No coincidence there. We'll see many more similarities than we will see differences as we move throughout this particular protocol's operation. So, let's see, we really don't need to dig into the configurations of these protocols, obviously, because we're just really focusing on design. So I won't give you details about the configuration of these protocols. Let's just stick to the high-level design criteria. OSPF version 3, yeah, once you master the version 4 OSPF version 2, once you master that technology, then mastering OSPF version 3 is very, very simple. There are more similarities in the protocols than there are differences. When we take a look at OSPF later on in this course, the version 2 for routing TCP/IP version 4, you're going to learn that it accommodates a lot of different environments. There's a OSPF network type, it's called, for broadcast segments. There's an OSPF network type for non-broadcast technologies like frame relay. There's a point-to-point network type. There's a point-to-multipoint type, and there's even a point-to-multipoint non-broadcast type. Guess what? All of these OSPF network types that exist for version 2 for IP4, all of those exist for version 3 for v6. So many more similarities than differences. When you look at EIGRP for version 6, we again see how similar it is in operation to the IP version 4 EIGRP flavor. BGP, we know it's unique in that we configure it in what's called address family configuration mode. But then once we get past that subtle difference, it just starts looking and acting like the BGP we will study in here. You typically are relying on an underlying IGP. There's a built-in IBGP loop prevention mechanism. There's a built-in EBGP loop prevention mechanism. It uses the same best path selection process. So we see this recurring theme. There's just many more similarities than there are differences. So one of the first things that we want to do is we want to go ahead and master the version 4 routing protocol for v4. And then once we've done that, it'll be very, very easy for us to master the design elements of the IPv6 version. But we said we have a challenge. We have a challenge when it comes to v6, and that is, how do we transition to IPv6? We can't just take down the internet and make the conversion in the course of an afternoon or 2 days or even a week. No, much more complicated than that. We've got to somehow allow the two protocols to be able to coexist for a long, long time. The designers of IPv6 technologies tell us that in our lifetimes, we won't see version 4 go away. Sure, we may see the pockets of version 4 get smaller and smaller, but we won't see version 4 go away in our lifetimes. So there needs to be rich transition mechanisms. And this is indeed given to us in IPv6, thank goodness. There is this wonderful concept of tunneling IPv6 traffic. We can do it in static tunnels, or we can do it in automatic tunnels. A great example of an automatic tunnel is a 6-to-4 tunneling mechanism they invented that automatically generates tunnels based on addressing that is utilized. Let me go ahead and elaborate for you on this tunneling concept. Okay, a key concept to understanding how we are going to transition smoothly and effectively into our IPv6 world. Let's go ahead and take a look at it. With this concept of a transition, we understand that for a long, long time, we're going to be stuck with these pockets of version 4. Okay, so I'll draw this cloud that represents version 4, right? I'll go ahead and draw this cloud that represents the v4 world. Okay, so what we're going to do is we're going to have these dual stack routers. That's no big deal. Like R6 over here and R4 over here. We're going to have these dual stack routers that run both v4 and v6, and they're going to be key players here in this scenario. Because they can run v4 and v6, they're going to help us transition by tunneling for us the protocols. So let's say that R6 connects to this v6 world and R4 connects to this v6 world. What we do is we create a tunnel between these devices. What the tunnel does, let's say it's a statically, manually configured tunnel, for example. what the tunnel does is it takes these V6 packets, and it encapsulates them inside a good old V4 packet. So the V6 packet is encapsulated inside a V4 packet on the R4 device, and it's sent through the network as a plain old V4 packet. When it gets to R6, R6 de-encapsulates the V6 that's inside the V4, and it sends it beautifully into the V6 domain. Wow. So it is very, very simple for us to tunnel these V6 packets inside the V4 cloud thanks to these dual stack routers at the edges of the V4 only infrastructure. Again, there are static tunneling methods you can use, and there are dynamic tunneling methods that you can use. The dynamic tunneling methods are great when you're going from some point to multi-points in the network. The static methodologies are great when you're going just from one point to another point in the network infrastructure. See how in this example that I gave, we are simply going from one point to another? We're going from R4 to R6? Yeah, because we're just going from R4 to R6, all we need here in this case is one of these simple static tunnels. But if you need to dynamically build tunnels quickly to many different potential destinations, then a dynamic tunneling option like 6 to 4, yeah, then you might want to go with some dynamic tunneling option like the 6 to 4 technology. All right. By the way, there is indeed another technology that you can utilize in order to do your transition to a V6 world, and it is one that students often get very, very confused about. Yeah, students really don't get this, and I can understand their confusion. The technology that we are talking about here is called NAT-PT. And they obviously get this confused very often with NAT. Don't confuse this for network address. Don't confuse this with network address translation, which is what we can use in V6, but would be very rare. It'd be rare that we would do IPv6 NAT because we don't need any private addresses only, right? We don't have this concept of RFC 1918 private addresses in IPv6. I told you earlier we have something called unique local addressing, but that's not really exactly like private RFC 1918 space. So we really don't need NAT. It's going to be rare that we would do IPv6 NAT. But what we are going to need when we're transitioning is a cool technology called network address translation hyphen protocol translation. This is another transition mechanism that will allow you to take your V4 addresses and dynamically convert them to V6 addresses and vice versa. Cool. So we can translate our V4 addresses to V6 and vice versa thanks to this exciting NAT protocol translation technology. Again, please watch out. Don't confuse it with regular old plain IPv6 NAT. Well, as a way of exam review, can we name and describe 3 types of tunnels? Wow. Wow, this is interesting, right? Pretty tricky. Well, let me give you a little more details about the different types of tunnels that exist out there. Okay? Give you some more detail on these tunnel types. We said there were static, right? Manually created tunnels. And we said these were great for point-to-point type of connections. Okay, of those, there is the ability to take IPv6 and put it right in IPv4. This is called an IPv6 IP tunnel. Cisco also refers to this as simply a manual tunnel. Whoop. And my sketch software just crashed. Whoops. That was the first time that happened to us in this class. Let's relaunch it. That was rather abrupt. All of a sudden, I had the classic general protection fault there. All right, let's try that again. So we've got our static. And one of the forms of the static is the IPv6 IP tunnel. Okay, we are taking IPv6 and we are encapsulating it directly in the IPv4. Cisco calls this sometimes a manual tunnel. Well, another type of manual or static tunnel that we can create is a GRE type. We can take the V6 and we can put it in a GRE encapsulation. Actually, we put it in a V4, then we put it in a GRE wrapper. You might say, why would you ever want to do that? That seems silly. If you can encapsulate IPv6 directly in IP packets, why would you want to go through the extra overhead that is involved with adding an additional GRE wrapper? Well, this has to be done where you're running ISIS in addition to these transition mechanisms that we are talking about. So if you're running ISIS and IPv6, you're probably going to have to do one of these static GRE tunnels. Now, for the dynamic IPv6 tunnel types, we've got that 6 to 4 that I mentioned. 6 to 4 is really neat and appropriate when you need to connect a bunch of different destinations dynamically utilizing IPv6. Very cool technology when we need to dynamically create a bunch of remote destinations. Another type of dynamic tunnel that is used is called an isotap tunnel. Now, an isotap tunnel is very unique to all the other tunnel types that we've talked about. It is actually a host to router dynamic tunnel. So this is the first of the tunneling mechanisms that we have spoke of that is not router to router. Yeah, isotap tunneling is dynamic tunneling so that hosts can dynamically get to their IPv6 default gateway. So there you go, folks. As Cisco Design Associates, you now know about 4 different valuable and important ways that you can tunnel your IPv6 traffic across our IPv4 clouds. 2 of the methods are static, 2 of them are dynamic, and one is really, really unique in that it is a host to router protocol. By the way, one last note. Since isotap is a host to router protocol, it's the one that will be soon fading away. Yep, it'll fade away. And we know why. Because all hosts that you find these days and all routers that you find these days, they're all being able to run IPv6. Haven't you noticed that? Any operating system you buy these days, any router that you buy these days, even some low-end little Linksys router from Cisco, it's all becoming IPv6 capable. So certainly the isotop tunnel type will fade out of existence long before these other site-to-site type tunnels fade away. Well, next up in our CCDA course, we're going to start a very, very fun section of the course. Students report it is their most enjoyable section. We're going to start to talk about our routing protocols. So very important when you go into an organization to make sure you are implementing the correct routing protocol for the job. I look forward to seeing you in our next lesson here of our CCDA Bootcamp.